So with system ID from a bode plot, you can find the poles and the zeros, AC gain, DC gain, and things like that. And you can just come up with a system response in a fairly straightforward way. The thing is doing this from the time domain can be quite difficult. It can actually, while it can be easy to see something that's underdamped, seeing the difference between over and critically damped, if I just give you two plots and a curve, you can't really tell. And a lot of times you would have to assume a fitting function of like the step response of a particular critically or over damped thing and just start sweeping poles and zeros until it matches. What today is really about is when you're looking at the time domain, can you get a general idea of what's going on, right? And so let's just start off in LTSpice, right? So on the midterm, if in the series circuit, if the damper froze, you'd have an you'd have an LC circuit. If you had it in parallel and the damper broke, you'd have an LC circuit. And so if I just do a step response of that in the time domain, you can see that it's oscillating, right? Now, however, let's just do a quick thing. If we're to do the bode plot of this, let's say we want to check it, right? So equals Vn. Laplace equals 1 divided by S squared plus 1. Right? So we should get the same thing. Oops. Ooh. Can't spell today. So you can see we're not getting the same thing. Okay. And that's for systems that aren't in control, trying to find the transient from the bode plot in LTSpice doesn't work so well. So if I have a bode plot, I mean, if I have a system response in the frequency domain, what I can do is come up with an RLC circuit, let's say if it's second order, and emulate that, right? So what if we actually had a pole on the right-hand side? Well, I can actually put -1 here, right? V check just stays flat, but notice we have exponential increase, right? Because you'd have the R1 being minus makes the transfer function negative, effectively. But that pole would be at -1 over R1C1. Since it's minus, it would be on the right-hand side. So that's how you can simulate. If you have a doubt about something, you can simulate that, right? Now, in this case, This is a fourth order low pass filter. And I can tell because there's some overshoot that there's some complex poles. Okay. Would be kind of hard to tell that this is fourth order just for looking at it. All right. But so the questions would be kind of different is what kind of filter is it? Well, it's a low pass because it starts low and ends high. Right. And we're going to get into that a little bit. And it has complex poles because we see some oscillation. All right. But what if what would happen if rather than bringing it in for negative feedback, I brought it in on positive feedback, right? You need to say have 1, 2, 3 inputs, 1, 2, I need a dummy. What would happen? It takes a bit to simulate. And what we'll see eventually is that there'll be some kind of exponential increase. And then it hits the upper power supply rail. Okay. So sometimes folks ask, what happens if you do that wrong or don't use negative feedback? Well, then the poles are in the wrong spot, right? We can take one of these. All right, so I have 1, 2 inputs here, 1, 2. So it should be balanced, but this node is now bringing, it's an inverting node, bringing it in on an inverting side. And so it's inverting the sign. Okay. And it does, a different kind of exponential increase. But if we just had that term missing, so 1, 2. You know what? Oops. Hold on. I think I made a mistake. I see your chat, but I think this was 1, 2, 3. This was 1, 2. I should have gotten rid of that. Okay. Let me see the chat. Right. Okay. Good eye, Nick. All right. So anyway, let's just get rid of it. One, 2, 1, 2, 3. And it's oscillating and with gain, and it's hitting the starting to hit the rails. We could simulate it for a little bit longer to see what happens. And so we have an oscillation. Okay. So if you want to see what happens when things are negative or missing, you can take a low pass filter you've designed and just start making things negative, positive, or missing. I still think that other example was unbalanced. But anyway. So, but for second order systems, if you really what I'm trying to say is, and I forgot my writing pad. Let's say we had H of S, right? And we'll make it a low pass filter. All right. So let's say I wanted to make that negative, right? Well, if this was a series circuit, right? That would equal 1 over LC, right? If I made C less than 0, right, then I can still make that positive. But if I made R negative, right, then that would be negative. I could have two negative things there, right? And yeah, in a series circuit, right, if I just set that equal to 0, then that part drops out, all right? And so by just using a series RLC circuit, you can simulate a second order circuit out of control pretty easily in LTSpice. Okay. Now, as exciting as that is, another thing that we want to do besides recognize out of control behaviors is recognize our classic filter responses: low, high, band, and notch, right? And there's something very interesting is that we don't actually have to take the inverse Laplace transform to find out what happens at time equals 0 and at time equals infinity. So let's say we have a low pass filter, keeping the constants easy, right? So the step response of that is H of S times 1 over S, all right? To find out what happens at 0, we multiply by S and then let S go to infinity, and we don't have to worry about complex numbers or anything. So basically, with the step response, right, the S's cancel. We're left back with H of S, and we let S go to infinity, and then this expression goes to 0, right? So yeah, for a low pass filter, it starts at 0. But what happens when time goes to infinity for a first order low pass filter? Infinity being time greater than 5 tau, right? Well, we do the same thing. We multiply by S. It really just cancels the step response, right? We let S go to 0, and then the output goes to 1. And so this idea that what happens at high frequencies affects the beginning of the simulation, and what happens at low frequencies affects the end of the simulation. Now this can, let's see. So if F equals 1 divided by S times 1 divided by S plus 1, right? I should be able to get the step response, right? And you can see, because I set it to tau equal to 1, that's where I'm headed, right? So at time equals 0, S went to infinity, we got 0. At time equals infinity, quotation marks, right? That's like S going to 0, and we got 1 over 1. All right, oops. So let's just look at the high pass. S divided by S plus 1, right? We take the step response. Of course, I know that we're going to multiply by S again. So really, the S times 1 over S is going to cancel, and we're right back with our original transfer function. So let's let S go to infinity. Well, that expression goes to 1. Let's S go to 0 for time equals to infinity. The expression goes to 0, right? So it's the opposite. So start at 1, exponentially decay down to 0. Okay? Now that we have the high and the low, well, for a second order filter, such as the notch, right? It's really, and this is only true for second order filters, right? It's the high pass node plus the low pass node, right? For fourth order, there's another node that you need to add in there. All right. Well, again, if we want to find the step response, we multiply by 1 over S. But then we're trying to find out what happens at t equals 0 or t equals infinity. So we multiply by S again, and it cancels out. So we're right back with our transfer function. So as S goes to infinity, right, these S squared terms dominate. You get S squared divided by S squared, it goes to 1. Now, as time goes to infinity, we let S go to 0. All the zeros drop out, excuse me, and the omega naughts cancel. It goes to 1. Voila. Starts at 1, ends at 1, and goes down. Now, there isn't really a theorem to kind of tell you what's happening in the middle, right? Although you could try to think about it a little bit, but the theory only really works at the extremes. All right. And let's see, did we get to band? Oh, we did. So when we're talking about the step response, right? Again, you multiply the transfer function by the step, but then you multiply by s, and then let s go to infinity or 0. So really, it's in cases of the step response, we're just looking at the transfer function. So we let s go to infinity, right? And the s squared will dominate the s, and it'll basically go to 0, right? At t equals going towards infinity, we let s go to 0, and it goes to 0 as well. All right. So it starts and ends at 0. What does Python say? There we have it, the band response. So if you look at the homework questions, right, you're first order circuits actually are fairly straightforward to do, right? I'm having to put in a square wave because, a step response, it goes up to 1 at t equals 0 and never comes back down for infinity time. Well, our Scopy and ADLM kits don't do that. We have to use square waves, right? So I have a square wave, and it's starting at 0 and ending at 2. All right. And the input is starting at 0, going to 1. The output is going from 0. Reverse, scratch that. The input is going from 0 to 2. So it's not a unit step response. It's a 2 times the step response. And the output is matching, going right up to 2 as well, right? And you can, how long is that taking, right? Because you don't see any overshoot, you can assume the simplest thing, and that it's like a first order, right? And then if that's the case, you can find out tau, measure 5 tau, find tau, that's 1 over omega naught, right? As a hint, damping ratios only exist for second order functions. Now you can have a fourth order function and break it up into 2 transfer functions that are second order, and then put a zeta in there. But really, zeta is a second order thing, right? And then, there's the gain, and you have to write that back, right? You should be able to see what this is pretty well, right? Based on, so yeah, if at time equals 0, we're going to 1, well, then what's happening to the transfer function at s equals infinity? So you do it backwards from the way I told you. Now here, is it first order, is it second order? Well, if you see this right here, there's this little bit of an S. And that's a dead giveaway that it's second order. Here, it goes straight up, right? That's like a first order thing. So since it's now second order, you can have like a zeta. But tau is only a first order thing. Say that again. Hello? Okay. Must have been a. Now, this is, you see oscillations, so it's definitely some kind of second order. But the thing about this is that just because it goes below zero and comes back up doesn't mean it's underdamped. This one you can see plenty of oscillations. And on exams and things, if it's underdamped, I try to show many oscillations so that it's not hard to tell, right? Again, we have something that starts and ends at zero, but there's this, it doesn't go right up to one, right? And here we start and end at one. And yep, I have a tricky one. And then I believe these are some review questions for the final. Okay. Hi, Mario. In fact, I already have posted practice exams. They're already there. I just wanted to get the name of this file, system. Yeah. So so that was kind of like our high level thing, but now I wanted to kind of take a step back. So we have the for first order circuits, what are the simplest thing? Well, an integrator, which is 1 over S, or a differentiator, which is just S. So if I take the step response, right, of an integrator, right, you're going to get a linear, right? And then if I have a square wave, and what it is, Desmos doesn't necessarily like these discontinuities, but basically you have a positive thing, it integrates, then when it goes to a negative value, it's integrating, but it integrates it back down to zero. All right. So really, if I gave you that there was a step response and you got a straight line coming out of it, well, then you'd have to say that that was an integrator. Okay. Now here, yeah, I have a lot of links. And I think so, like, here's the phase and magnitude and phase of a low pass filter, and it's just, you can see everything going back and forth and kind of slowly putting you to sleep. There's the high pass. And then, so the purple is the high, the red is the low, and I'm just changing omega naught. And you can just see that 5 tau is changing, right? All right, that's kind of hypnotic, so I'm going to have to stop. Okay. Now, for a low pass filter with no gain, right? The red, the damping factor is 10. And when you see this on an exam, right, see how the poles are like really separated, right? It's kind of easy to see that it's overdamped, right? And then in this case, it's underdamped because it's at omega naught, the magnitude is even greater than 0. Now, but here's a trick. Critically damped is 1, and so that point would be minus 3 dB, no, minus 6 dB down. But if the damping coefficient were 0.707, it would be minus 3 dB down. So you can have complex poles and not have a peak, right? But in the time domain, right, here's the low pass. And what happens is this slow pole is so much slower than that fast pole that it almost makes it look like a first order step response. Then this is our critically damped, right? Now, if zeta were 0.707, this point would be minus 3 dB down, and there would be a little bit of overshoot. And this kind of happens on exams, that people just think no peak, it's not underdamped. No, it's if that peak for a second order system is greater than minus 6 dB, like minus 5, 4, 3, 2, 1, 0, right? Then it's underdamped. And underdamped will always show a little bit of peaking in the transient. The blue doesn't because it's critically damped. Now, yeah, here is the going through the whole equation for red is 2 different poles, blue is 1 repeated pole, and then green is 1 complex pair of poles, right? And so you can see that it's, a lot of actually programming to get this right. But you can see that they should all three should start at 0, because at S equals infinity, right, it's headed towards 0. And you should see they're all going to head towards 1, because at S, as S is going towards 0, the output is going towards 1. Now, this is what I wanted to talk about with the high pass. Well, the green is very obvious, a lot of ringing, it's clearly underdamped. Notice the blue, it's still critically damped, but it crosses 0 once and then settles. And then, interesting thing is that for the high pass filter, it's the fast node that really dominates the response, and so it decays very quickly, but it doesn't go past. All right. Again, there's everything with Desmos, and here are the equations. With the bandpass, right? Everything starts and ends at 0, but look at the red, the overdamped. What's going on is that the slow pole, right, or the fast pole is dominating so much that it almost looks like the step response to a first order high pass filter. You'd have to zoom in and you'd see that that red line is coming over a little bit. All right. And then we have the notch, right? Where it starts high at some value, dips, and then settles. Okay. Now, what I have here is some data that I measured off of a second. Oh no, let me make sure I don't. Yeah, this is a second order filter, but it's measured data. So it's not perfect. Notice that the phase, right, it has 0, but it only really goes down to minus 175. Well, what was going on is that the magnitude was getting so small that I couldn't measure it, nor could I measure the phase. So normally in a LTSpice plot, I'll simulate so where you can see the phase even out, and here it doesn't. And so also you'd say, well, I want omega naught. Let me go from minus 90 and pull it across. But again, the phase is telling me, since it's going negative, that really I have a non-inverting low pass filter, right? But it would be very hard to get my true omega naught from it. So I just use the magnitude method. So here's the DC gain. I draw a line out. Here's this AC slope. They intersect and I pull omega naught off from there. No class on Wednesday, guys. Thank you for coming today. So anyway, you find omega naught, right? So in this case, it was frequency. So F naught was 350 kilohertz, so omega naught was 2 pi that. So that's one thing you need. The gain DC, it was 0, so it's 1. And then HJ omega naught, you know, at H, I measured that to be 5. You can't really tell how that it was 5, maybe from this graph, but I had the data points and I was able to look it up, right? So if at omega naught, the magnitude was 0.56, the damping ratio was 0.89. So it's got complex poles, but it's not exactly a Butterworth filter. I was aiming for a Butterworth, but I didn't have the components that day. I had to make do. Now, then what I did is I imported the data into LTSpice and then really tried to match everything, right? And so I adjusted things until I got a much better match. And then looked at the transient response. And you can see there's this little rise. So at as zeta equals 0.89, there is a little bit of overshoot. Okay. So I'm thinking everything is working really well, right? Then I go to measure it. And maybe you guys already saw, you're just being polite. You didn't see the mistake I was making. But this is the output, the yellow, right? But here's my bode plot. I mean, that's a low pass filter, right? I mean, everybody can agree to that, right? But how is it possible that I'm getting a notch filter on my output, right? And so that's kind of, why is it that I make a big deal about all the different filter types is green, yeah, that looks like a low pass filter, but green wasn't. So green is the output, right? But the yellow was the input, which should be a step, but in fact, it's a notch, right? Well, what had happened was, and that's why I say you guys probably all realized, saying, "Well, hey, professor, you have 77 ohms there. One, you say you always got to have 2K." I'm like, well, yes, I say that. I didn't have 2K that day, and I didn't have an inductor that would work that way, right? But the bode plot is working, right? This really worked. It's a low pass bode plot, but I wasn't taking into account the fact of the 50 ohm series resistance. Every function generator has that. So in fact, this was the input, right, to the oscilloscope after this 50 ohms, which if you take the voltage division, you see that eventually it looks very close to a notch filter. Not a perfect notch filter, but that is what's going on. And then here's the thing. If I thought that my transfer function were these three values, well, no, that series resistance is affecting the time domain response. Now, the reason why the bode plot worked is that I was just measuring the delay and ratio from here to here. So it didn't matter that it was dropped. It didn't matter that it was acting like a notch filter. It was able to, and Scopy will do the same thing. All right. Anyway, what you need is a, so if you wondered why I was using like 5.6 millihenries, that's so I could get this up to 2K, and that then when you work out the math, that voltage division is hardly anything. You can't notice it. Okay. Okay. There seems to be a lot of confusion. I am grading. It's just, sorry, it's just going slowly, right? But there seems to be kind of a lot of confusion that derive the relationship that will make the above circuit have a gain of 17, right? And then show why the circuit is over, under, or critically damped. So there's two parts to this question. When will the gain, if that op amp is ideal, then the gain is going to equal 1 plus Z2 divided by Z1, right? We already kind of know that, but what, is going to, what conditions is going to make that happen? When is it going to act ideal? Well, we have a frequency dependent model, so we need to kind of come up with a frequency dependence, right? So in this case, H of S, and I'm just going to say AV open loop gain. In that case, it's 1.7 times 10 to the fifth, right? And we have S plus P1 S plus P2. That's the transfer function, okay? Now, in order to find out anything about this system, we have to put it into the control systems type equation where we have okay. Now, in this case, those impedances are just resistors, right? And so it's just kind of a special thing called constant called beta, right? So that's really the voltage division of those two resistances. Okay. So we have G of S, we have H of S, and we know that that's the numerator, which will appear here. Right? G of S is beta, which will appear here, because when I multiply this denominator through this equation, right, the denominators will cancel out, and one will keep that denominator there. So those two poles will appear. All right. Now, what we need to happen is if the open loop gain goes to infinity, then beta open loop gain goes to infinity, right? And that this part just drops out. But a better way to say that, because now S equals J omega, it's a complex value, is that the magnitude of those two things has to be much, much less than this value. Now, if that's true, right, we get this, which then we get this, 1 over beta, which when we manipulate it, we get. Okay. These are the conditions to make this happen. So it's not enough just to say QS or something. You have to say what's going on, right? Now then the over under critically damped, well, all we need is the denominator. It's second order, so it's better just to put it in terms that we can understand, so that we can use the quadratic equation, right? But we'll have S squared, we'll have the sum of these two poles, and then the two poles multiplied. Okay. So P2 times P1 plus P2 S squared, right? And then we have this portion right here, right? This is the extra bit. Okay. Well, now we really need just to know what's inside the square root, right? Because we're just asking, is it over under critically damped? So we just need to know the number of poles. Right? And so for AC equals those two things, and B equals that, and then, you know, you would just calculate out okay, that's the full blown solution. You would have used your numbers. Well, you know, don't say things like that, because I haven't necessarily graded everybody. So, you know, don't discount it. Right? I have to look at things like process and procedures. Okay. But it was yeah. Okay. There are homework solutions and old exam solutions with this problem. Sometimes it's solved just with variables like this. Sometimes I have numbers there. Okay. Now, this is a fourth order low pass filter because I'm taking out here. All right. Now, if I had just left it like low pass, in this particular question, I didn't say high or low pass. I just gave I just gave this. I didn't tell you what it was, right? So you couldn't really just label a node, right? So really, you had to know where you were taking it. Oops. So for the one that I just showed, we were getting s cubed, right? S to the fourth would come here. S to the cubed would come off of this node, and it's inverting. And so I just have to kind of invert it. Okay. Now, the other one, sorry, it's a bit ugly, right? If you see, everything is, that's an even power, that's an even power. And then if you know that structure, you know that that would be an even number of integrators to get to that low pass node. So that means I'm coming off of this node, and this node, none of which are inverting, right? It's a little ugly. Okay, 1, 2, 3. Now, really, you could have put one dummy there or 3. I know that you could adjust that resistor. All right. Now, there was something where I don't know what's going on. Maybe just lack of sleep. But people, I've been seeing this a lot. Okay. Don't do that. Okay. But really, the whole question is basically where do you take the output and how do you deal with it? Because this is almost from like memory. There's so many problems out there where the structure is there that can just be kind of copied. The majority of the work is, the thinking is in here. Okay, so that's a bit of review of that. I guess this one seemed more confusing. It's kind of like either you got them all right or you got them all wrong. Okay. But all the signals in FFTs were the same. It was just some had them in one order and another. All right. But here I have what looks like to be a pure sine or a cosine. So I should have one thing at a frequency. Right. This has 1, 3, 5, so it can't be that. This has something at 2 hertz and something at DC, but there's no other sine wave in there. This has 2 sine waves, and this has many sine waves. Right, so this one has to go here, right? And you can see that it's been shifted up, and there's our DC, there's A naught, right? Now here, this one might be the difficult one, so you could just leave that for last. Now this one, it goes from -1 to 1. It's 50% duty cycle, so there's no average, right? It all cancels out. But we know square waves have an infinite number of odd, 50% duty cycle square waves have an infinite number of harmonics, but you know, this one has no DC offset. So infinite number of harmonics, infinite number of harmonics, DC offset, no DC offset. This one goes here. This one does have a DC offset, right? Its average is 1. And so now you can see that, yeah, this had 2 cosines in it, or 2, whatever I had done, 2 sine waves. 1 at 1 and 1 at 4. Okay. I'll throw it open to any questions, but that was, or oh, before we do that. So really, if you look at the homework, that's more like what would be on the exam. I have a lot of things here. I have a lot of videos, right? Because I guess I just don't delete any video. All right. I have examples on first and second order video, other, you know, specific videos if you want to just not look at everything. But that thing where I'm backfitting parameters to find out whether, you know, it's over, under, or critically damped, that is not on it. That's too much. All right. Just so you know, I might delete some things, right? Now, the fact that LTSpice doesn't do well with out of control systems from the behavioral source, that's not really on the exam, but if you want to check your work, right, because you can, you know, make an RLC circuit, you can put in negative values where you want, you can, you know, you can't set a resistance to 0, but you can either remove it and replace it with a wire, or set it to like 1 nano and it'll effectively be 0. All right. So that's just how to use these things. And maybe I think I have to go back and check. That might be too much information, too many videos. Okay. So I would start with today. And really, like if you look at activities, I'm saying here's what to read. And this idea, right? System ID, like as a homework, isn't in the book, but these 2 things here, setting S to infinity, 0, right? After multiplying the step response by S, right? You can figure out the beginning and ending of any linear system. Any questions? On,
Yeah,
I guess,
so
on anything, yeah.
I was curious. So it does replace the final midterm part 2 also replaces the midterm 2 grade, right?
If it's higher, yeah.
Oh, okay.
If you look at, since I have Canvas open, you see how there's 3 parts, but it's really 1 10-question final exam. 3 questions from here, 4 questions here, 3 questions here. If this percentage is higher than the original, it replaces the original midterm. If this is higher than the original midterm, it replaces it. And this is just that everything since midterm 2, which is really system identification, modulation, and more applications.
I see. So for the fast Fourier transform, are you gonna ask just like estimating the coefficients and stuff, or are you going to ask us to integrate on the test? And
I haven't decided, but
oh, I see.
you know, I'm a random test generator as well, but you can see just about anything I've ever asked on previous questions, right? So you can see sometimes I do this, sometimes I do that, but like a lot of times the question of mixing and matching for your transforms isn't there. You'll find more, hey, here's something, tell me what to keep for a low pass. Tell me what to keep for a high pass, notch, this and that, right? And you pretty much all the things I think of are there. I haven't gotten into, you know, do a quarter duty cycle thing, right? You know, calculate the coefficient. Actually, you'll see I never say, here is a function, calculate the coefficients, like pure integration. Now, yeah, you've seen it where I'm asking you to estimate a few, right? But not like that. So I wanted to circle back to Sam's question about how to find the damping ratio in a transient response again. I didn't really say, because it's actually very difficult. What you can tell is for a low pass filter, if you see any overshoot, then it's underdamped. But critically damped and so if your question is, tell me the exact damping ratio, I'm going to tell you that that question, you know, extract some exact value isn't going to be on the final. It's not, you know. So here, right, I have 3 different damping ratios. And notice this damping ratio is so large. I have 2 different poles, and the slow pole is the one that's dominating. So this almost looks like it's first order. If I zoomed in, you'd see a little S type thing, right? But even here, I think it'd be very hard for you to tell that this was actually a second order filter and not a first, right? So if I just gave you this red plot and nothing else, or this blue plot and nothing else, you can't really tell. Here, you would just say the damping ratio is definitely much less than 1 because there's a lot of oscillations. And you can actually measure this decay and the peak to peak and actually do a fairly good job of estimating the response. It's just what I have found is that it's very hard to do this. So I don't ask it like that. So it's more, is this a high pass or a low pass, notch or a band, which you should be able to tell, right? And then if I'm super obvious, underdamped. Okay. Is that good, Sam? It's not like homework 11 where you come up with a number. Okay. Maybe Sam had to go. All right, will they have the same layout? You decide for yourself. You can look at my old exams and see. They have many of the same things, but sometimes the questions are different. Okay. So I'm not quite sure what you mean by layout, Rudy, but it's not necessarily the same question like the damper breaks or freezes, right? Oh, thanks, Sam, for answering. Okay. How would you find 5 tau for an underdamped? Okay, that's a great question. I guess I wouldn't, because tau, that 5 tau, is only a first order thing. Where if I know it's first order and it takes a certain amount of time to get to 1 or a certain amount of time to get to 0, that's 5 tau. There's not really a 5 tau, because look at here. There's for underdamped, overdamped, there's 2 poles, right? And there's 2 exponential decays, right? So which one are you going for? Then for critically damped, I have an exponential decay, but then I have an exponential decay that's scaled by omega naught multiplied by t. And now, yeah, I found that I can kind of estimate omega naught if it's 7 instead of like 5. But this one you can measure everything and actually get it. But it's just, that doesn't seem to be what's really necessary. Like, I have a system and I'm trying to make sure that I've extracted the right thing. And, you know, I had an interesting thing on the input, because this doesn't have any overshoot, right? Well, that's because the input isn't really a step. So this is a real output, but it's not really working. It's not really showing me the step response. But here, in theory, that little overshoot is a complex pole. Take care, Andre. All right, I know everybody's got to scoot to 112. So have a good day. Have a good Thanksgiving. Please stay safe.
Have a great break.
You too.